The last type of logical geospatial data model I want to discuss is the triangulated model, in which we can model geographic objects as a continuous and irregular network of triangles. And so the triangulated model includes triangles, or also what are known as faces, that are located on a three-dimensional Cartesian coordinate system. So it's not just the x and the y values, but it's also the z values. And you can see in the example on your right that each triangle has three nodes that are represented by x, y, and z coordinates. And then those nodes are connected to form a triangle in which the attributes elevation, aspect, and slope are stored. And so the triangulated model really lends itself to modeling topography or terrain in a geographic information system. And so all triangle faces in this model include elevation, slope, and aspect. The elevation is interpolated between triangle points. So if I click anywhere on the face of the triangle, the elevation is actually going to change. The aspect and slope does not, because it's the same for the entire face. We can also use fill polygons to assign other attribute values to triangle faces. When we do that, it must be an integer, and it can affect how the underlying triangles are structured. If you look at the example on your right, you can see the top layer represents a triangulated model with the elevation attribute symbolized. The bottom layer represents some type of other attribute, maybe forest cover, that has been assigned to the triangulated data model. And so there are a number of advantages and disadvantages to the triangulated model. Some of the advantages include modeling variations in terrain, which allow for more triangles to be utilized for variable surfaces and fewer for consistent surfaces. So you can imagine if I'm modeling the entire state of Colorado, I've got a lot of changes and variation in terrain in the western portion of the state and not very much in the eastern portion. And if I'm utilizing a raster data set, I have to either decide on utilizing a small cell size so I can capture all the variation in the western portion, but then I have a lot of duplicate or unnecessary resolution in the eastern portion of the state. Or if I use a triangulated model, I can use a bunch of small triangles in the western portion and large triangles in the eastern portion that are all part of the same triangulated model. So it's a little bit more efficient way to represent elevation. You can also represent roads, rivers, and lakes with surface features that are basically burned into the triangulated surface. The triangulated model displays well at different zoom levels. It's typically utilized to cover small areas in detail, although I have seen it sometimes utilized for larger areas, for example, like an entire state. The last advantage is that the triangulated model makes for very crisp display quality. Now, some of the disadvantages include that it can look triangulated. If you zoom all the way in, you can actually see the triangles. Even though you can relate the triangulated model to an attribute table, it can be very difficult. Triangulated irregular networks cannot be stored in a geodatabase, but terrains can. We'll talk a little bit about that in just a second. Last, if we're utilizing elevation data to create contours, we typically want to use a raster digital elevation model because it creates smoother contours. If you create contours from the triangulated model, the contours often look jagged. In ArcGIS, we typically only work with two triangulated data formats: triangulated irregular networks, or TINs, or ESRI geodatabase terrains. Both of those formats can be created, deleted, read, and written in ArcGIS. Now, what are the difference then? Well, a TIN cannot be stored in a geodatabase, but a terrain can. A 10 does not allow for pyramids. So you can imagine when you look at Google Maps and you're zoomed all the way out to the world, and then you zoom all the way in and then zoom all the way back out again, you notice how the images tile in? That's pyramided, so that it speeds up the display whether you're zoomed all the way out or zoomed all the way in. With a triangulated irregular network, you can't do that. And so sometimes the display and analysis can be really slow. For terrains, it allows for multi-resolution terrain pyramids. So if you're zoomed all the way out, you can use large triangles, and if you're zoomed all the way in, you use small triangles. In doing that, it allows for very fast display and analysis. The thing I like about TINs over terrains is that it is a very common format, and there is full support for 3D geoprocessing, not just in GIS, but also, for example, in computer-aided drafting software. Terrains are a much less common format, and there's limited support for 3D geoprocessing. There are even some geoprocesses in ArcGIS that can only work on tins and not terrains. So which format you use depends on what you're trying to accomplish.